This is IAQ Radio, Indoor Air Quality Radio, the voice of the indoor air quality industry, with your hosts, Radio Joe Hughes and the Z-Man, Cliff Zlotnick. And now, Radio Joe Hughes.
Good day and welcome to IAQ Radio Plus, episode 681. This week, we welcome Lisa White, Associate Director at the Passive House Institute US, Phius. This show is going to be a great follow-up to our recent discussions about the Internet of Things, sensors, and the Electrify Everything movement. Lisa did a well-received presentation at summer camp with thoughtful insights on how changes to the grid can be coordinated with changes in buildings and take advantage of the moment. So before we get started, let's thank our sponsors. They're the reason we can continue doing the show. And remember, we continue the discussion after the show at afterthoughts.iaqradio.com, sponsored by First OnSite. Our marquee sponsor is First OnSite at firstonsite.com. Our association sponsors are the American Conference of Governmental Industrial Hygienists, ACGIH.org, the American Industrial Hygiene Association, AIHA.org, the Cleaning Industry Research Institute, CIRI Science.org, the Institute for Inspection, Cleaning, and Restoration Certification, IICRC.org. Industry sponsors are AEML Laboratories, AEMLINC.com, Particles Plus, ParticlesPlus.com, TSI Inc., TSI.com, Sunbelt Rentals, SunbeltRentals.com, April Air, April, AIRE.com, Healthy Indoors Magazine, HealthyIndoors.com.
And now you can win a cool prize. It's time for the IAQ Radio Trivia question. Be the first to correctly answer. Simply email your answer to czlotnick@cs.com. Or if listening live, just text your answer from your computer. And now, here's the Z-Man.
Hello, everyone. I'm sorry to report that no one identified Dale Kleist as the Ohio State grad student whose accidental discovery was a breakthrough in making fiberglass, which is our most popular insulating material. The IAQ Radio Trivia question for today, November 11, 2022, has been sponsored by TSI Inc., an industry leader in the precision instrumentation of monitoring indoor air. Learn how to expand your IAQ investigations at TSI.com. Here's today's IAQ Radio Trivia question. Name the voluntary standard used in Switzerland for reducing a property's eco footprint. Back to you, Joe.
Okay, Lisa White is the Associate Director and Technical Lead for Phius Institute, or the Passive House Institute US. Ms. White has been with Phius since 2012. She led the building certification review team for 7 years and is an instructor for the Certified Passive House Consultant Training and the WUFI Passive Energy Modeling Software Training. She also has a degree in environmental sustainability with a minor in architecture from the University of Illinois at Urbana-Champaign and a master's in energy engineering from the University of Illinois at Chicago. Welcome to IAQ Radio, Lisa.
Thank you so much, Joe.
It's great to have you. You came to my attention when I saw that you were speaking at summer camp. I was hoping to see you there, but unfortunately, my ride got COVID, or his wife got COVID, and we didn't want to take the chance, so I didn't make it. But anyway, tell us a little bit about Phius. We have never done a show on Passive House, so if you could tell us a little bit about the organization and your position.
Sure. So to start, Phius is a 501c3 nonprofit whose mission is really that every building supports the health of people on the planet. And we're trying to do this by making high performance passive building mainstream. So the organization itself is, we do training. We train professionals, architects, engineers, builders, commissioning specialists. We certify buildings and set building performance standards, which is kind of the passive building standards, passive house standards. And we also certify components that go into buildings. So like windows, or we certify their data, windows, ventilation equipment, panels, things like that. We also have research groups. So we're kind of research and policy initiatives where we kind of key into other things happening across the US or around the world. And we have a membership organization called the Phius Alliance. So we're kind of a split in terms of our staff. A lot of our staff is technical staff, and that does project certification reviews. We set that standard for building performance, and people will submit their projects trying to achieve certification, kind of like LEED, but very different in terms of its focus than LEED. And then a lot of our staff is focused on training, and then the other end kind of supportive and marketing communications and trying to make this really mainstream market standard. And my role, I'm associate director, as read my bio, but most of my time at Phius, I'm on the technical side and have worked on standards development, setting those performance metrics for the buildings, and reviewing project submissions from teams trying to achieve certification. It's a pretty intensive process where you review energy models, give feedback, make sure the project is in line for certification throughout the design and construction of the project. Now I'm more so kind of oversight and organizationally working on data and more like handling inter-operations between departments, if you will. We've grown a lot since I started at Phius about 10 years ago. So my role has kind of changed a lot. I kind of touch every end of the organization.
I don't remember exactly how you worded this. It was just a second ago, so I'm getting old, okay, obviously. But you mentioned that Phius was a little different from LEED in some ways. Can you kind of give us some idea,
Sure.
a little more meat on the bones there?
Yeah, sure. So LEED is generally the certification standard for buildings that everyone has heard of, even, your mom, everybody has heard of LEED. So I always try to refer to it relative to LEED. So LEED is essentially a point-based rating system where you get different points for different elements of like green building, and energy might be one of those buckets. Health might be one of those buckets, but you get different points, and there's different, ratings where you might get platinum, silver, gold, and all of that, depending on how many you add up to. And like site planning, bike racks, those things get you points. Phius is a pass-fail standard that's really focused on energy. So the kind of in the LEED certification and the energy part, if you got Phius certification, you'd get all the energy points. There's also elements of the Phius passive building standard that are related to health. We use EPA Indoor Air Plus as a co-requisite program for our certification. So there's a lot of things inherent to what we're doing with our certification that would earn you points in other places in LEED, but LEED is really zooming out, trying to look at kind of a green umbrella, where Phius is pretty focused on basically making a quality and healthy building with really reduced loads in the goal of kind of getting to reducing total emissions, getting to net zero, that type of thing. But thoughtful design to reduce energy loads in buildings. And then we kind of tag on those other programs.
And do you get like a plaque on your building or mentioned somewhere?
Yep. Okay. We have a project database on our website where all the certified projects are listed. And once you're certified, you get a plaque. Everyone loves the plaque.
How popular is this right now? I mean, LEED is very popular now. WELL is becoming a big deal. How does Phius compare to those?
It's definitely not as big, but it is growing at a exponential rate. So in terms of projects, we have I'd probably say about 1,200 projects maybe total, about half of those fully certified, the other half are in the certification process. Many of those are large or any scale of multifamily buildings. So in terms of like square footage and units, it's quite a big impact. I think we're at like 16 million square feet. Most of that in the US, some of it in Canada, a little bit in Mexico. So we got a little bit of spread outside the US and Canada, but mostly US and Canada. But like relative to LEED, it's quite small. But there's this like certification growth chart where you can see year after year things are just doubling. And with all the different policy initiatives that are happening, writing passive house certification into stretch codes or low-income housing tax credits for multifamily, that's a big thing that accelerated growth. We're seeing, just like I said, exponential growth in this concept and in this certification.
Interesting. Now, in your presentation, it was called Grid Building Interaction, Microgrids, and Passive Building. First, could you give us kind of your thumbnail of what passive building is?
Sure. Yeah. So passive building or passive house, you can kind of use them interchangeably. I try to avoid using the word house because it applies to all building types, all building typologies, like these strategies apply to all buildings. So passive building is basically a design methodology where you use passive building principles to reduce energy use in buildings and create a comfortable, healthy, resilient building. And the principles kind of revolve around 3 different control strategies. So you have thermal control in the enclosure by super insulating, or more insulation than code, and making that insulation continuous. So focusing on minimizing or mitigating thermal bridges. You have air control in the building by air sealing the building. This is one of the pass-fail metrics for passive house. So a super airtight enclosure, they must validate that with a infiltration testing, both pressurization and depressurization. So making the enclosure really airtight, and then placing intentional openings in the enclosure for a balanced ventilation system with heat recovery and filtration. So you're kind of controlling the air that's coming through the enclosure as well as the air that's coming in through this ventilation system. And then there's solar control. So that's basically a combination of picking the right window performance in terms of solar heat gain and the right window optimization for orientation, as well as the shading strategies. So allowing for solar gain when you want it and blocking it when you don't. I do want to mention that passive solar and passive building is not the same thing. There's some of the same concepts, but passive building is kind of like the step above that incorporates a few more important strategies like the balanced ventilation. Passive solar was more a movement about 50 years ago where you would have a lot of thermal mass and big south glass and try to just heat the building with the sun. The concepts are the same, but in terms of like the balance and the optimization, we've come a long way since just wanting all of the sun all the time. That was a very heating dominated biased approach. Like Canada, northern areas of the US really could take on that approach, but that doesn't work for Florida, for example. But passive building itself works everywhere.
So let's get back to the presentation itself. John, if you could go ahead and pull up slide 6. I guess I watched it. I read through the slides, and I guess my impression was that the goal was to not just look at, to take this moment where we're looking at the grid, we're looking at things like microgrids, we're looking at sustainability, we're looking at comfort, we're looking at, all these different things, but to also come at it from the bottom up, from the building side up. And that you feel like this is a great opportunity right now for us to fix some issues that we've been dealing with for a long time, and at the same time, kind of do it from the bottom up instead of just top down.
Yeah, exactly. I mean, it's really, I feel that the grid and the buildings and the wires that connect them have all kind of operated in silos, not really considering the impact of one another. The grid has been required basically to provide reliable, uninterrupted power service to all of these buildings, but the buildings don't necessarily think about the capacity and the infrastructure required to meet that load. And there's a lot of opportunity when you just think about, okay, what can this building do to actually, if it actually knew what was required on the other end, basically. And because there's a lot of things changing with the grid, which we'll get into, there's a lot of opportunity to just think about this as more of a holistic concept rather than like, this is our power generation and this is the use. Usually you think about the grid as the supply side and the demand side. So what's generating the power and what's using the power. But those can, we're losing a little bit of control of the supply side with renewables, which I'll get into. So we need to add a little bit more control of our demand side. And actually, before we dive into this, just to kind of reinforce passive building, could we jump to slide 32?
32, John.
Yeah, okay. So I just wanted to reinforce, so we're using these passive building strategies, the insulation, air control, thermal control, radiation control, to take what a typical building might look like. And this is maybe Chicago, big heating loads in the winter. This is an annual load profile. And, roughly half that peak cooling load in the summer. And we're using passive building strategies to not only reduce those peaks, but reduce the amount of time and the amount of heating and cooling you need over the course of the year. So that's really what a passive building is doing. And I didn't say that out loud. So I wanted to make sure you understood that concept before we talk about that into the whole picture with the grid. So
I think that's helpful, and it's also helpful to get the understanding that you're looking at changes that are occurring anyway. Why don't we go ahead and do them in a more coordinated way and kind of allow the buildings to talk to the grid, I guess, exactly. And that way we can exchange information back and forth and do a better job of growing this and fixing this issue. But let's go back and talk first about the grid.
Yep.
I think a lot of people are more familiar now with this and the fact that we have 3 grids, not 1 in the United States.
Yep. Yeah, so we have 3 different interconnects, West, East, and Texas. The Texas part, I think, surfaced in the past few years when people were like, why is Texas on its own grid and all the issues they're having. So they're not connected. They all operate at the same frequency, but just like slightly off from one another. So it's not that we can even just connect them. You'd have to shut everything down, which can't do, and then try to restart it all together. So they're not connected. But you could potentially, I think, transfer power over, you could transfer DC power, I believe, over the lines, but we won't get into that. And then the different regions of the grid are operated by different ISOs, or independent service operators, that basically look at the demand in that area and are responsible for meeting that.
Okay, let's go to the next one, John, which is, I think, going to be 11. And here you talk about how the share of renewables is growing.
Sure. Yep. So right now, let's see, about 70%, 75% of our resources are fossil fuel based, or at least dispatchable, not renewable energy, natural gas, coal, nuclear. And the renewables share is growing significantly, and that's mostly solar and wind. The wind could be onshore, offshore, but generally a centralized, wind farm. And the solar could be a combination of things. It could be centralized solar farms, so big arrays of solar, community solar, things like that. It could be concentrated solar power. There's only some places where there's actually enough like ground area to do this, but there's a lot of that in like the Southwest Arizona area. And then a lot of rooftop solar. So individuals with their homes putting solar on their roof. So, but generally it's all the solar photovoltaics in different flavors.
Let's go to the next one, John. This is how we're looking at the seasonal load profile. And I think this is really important to some of the stuff coming up later.
Yep, it is. So when we look at the entire grid and the different like regions that the operators have to basically meet the load for, it's fairly predictable what the load is going to look like in the winter versus the summer. And it's also fairly constrained to the different resource types that are available. So in the winter, there's typically base load, an intermediate load, and then a peak, maybe a morning and an evening. For the summer, there's just one big peak in the day. And the base load is generally met with coal, nuclear, and some renewables, but it's these generation resources that don't have flexibility in terms of their output. The output from these resources is flat. And can't really change. It can't change, like if the sun goes up or down or a cloud moves, it can't change to respond to variables in weather or load. So that's just the flat load, and it stays the flat load. The load following resources meet the intermediate load. This is generally natural gas. CC means combined cycle. It's just a more efficient way of producing electricity from natural gas. And then some renewables, they're like hydro, where you could consider hydropower from basically pump storage to be energy storage, or to be dispatchable when you need it, to follow when that next increase in the load happens. And then we have the peak load, and this is what makes electricity really expensive. So the peak load is when every building is running as high as it might be in the winter. This would be probably from heat. And the peaking plants are the plants that are available and running, spinning year round, like spinning reserves, but you only actually extract electricity from them during these peaks. But we have to pay to maintain and operate these, even though they're rarely being used. In the summer, kind of same thing, right? And right now, the US grid peaks in the summer because of the higher amount of electricity used in the summer from cooling loads. But we're going to get into that. That's going to change as we electrify buildings.
All right, let's go to the next one, John, which I think is the next slide.
Okay,
The
so
load duration curve. That's a new term for some of our folks.
yeah, what we're basically looking at is the capacity. So we talked about capacity. I'm talking about the generation resources. So coal, nuclear, natural gas, renewables, hydro. And the amount of capacity is like the output of those. So the base load capacity is used 100% of the time. Those generation resources stay at a constant output. They don't change. They're used all the time. The load following capacity is used, a little bit less. And during times of higher use, or during times of higher peaks on the grid, more of it is used, but it's not used to its maximum. Meaning that if it ran all out, the capacity that we had load following, it would be too much. And then the peak load capacity is rarely used, but there's a good amount of that capacity requirement relative to like load following, right? So with the US grid right now, we have about 2.5 times to 3 more generation capacity than we need if everything ran all out all the time, right? If we just said everything run, or 80% or whatever. If we said everything run, it would be too much energy. And the reason is because we need to size the system to meet that peak. So if we ran everything, we'd have 3 times more than we needed. And if you think about buildings, the way to connect this to a building crowd is you think about a heating system and you model a building and calculate a peak load, and then you add some sort of redundancy, right? To make sure that peak load is met. You increase the system size. And the peak load is only happening for, X amount of hours per year, maybe a couple days per year is that peak load happening. That's happening at the grid scale. So for 363 days of the year, we don't need that peak load capacity. Same way as like a heating system. We don't need that peak capacity. But when you consider how that has to multiply out by all the infrastructure required on the grid, it's a pretty significant deal. It's not just, I have a 12 kBTU instead of 9 or whatever, 18 instead of 24 in my building. It's multiplied across the infrastructure in the US grid.
I guess this really catches your attention because we're generating 2.5 to 3 times more than what we need. If we could figure out a way to kind of balance that out, that's where the low hanging fruit to some degree, maybe it's not low hanging in that it's not as easy as it sounds, but how we cut the amount of capacity in half and better even out how we use that capacity, that would cut emissions tremendously real quickly.
Right. So we're not generating that much, but we have the capacity and infrastructure to be able to do that. Correct. Which is the money, right? It's not necessarily the emissions, but it's definitely the cost.
The cost is okay. So I should be looking at that more now, but we also do generate more than we need probably. Well, I guess I don't know. That's a question. Are we?
Not necessarily.
Okay.
Yeah, not necessarily. Generally, there's a demand on the grid, and then the generation capacity meets that. What we are having happen, and I'm not sure if we're getting to it later, is there is renewable energy that's being over-generated and can't be used due to some constraints. I don't know if we're going to talk about curtailment later. Maybe I should hold that or talk about it now, but we have renewable energy that's available, and either due to transmission congestion or meaning there's not enough wires between the centralized renewables and the load to get it to the load, or the base load capacity can't move down, that we have to curtail this emission-free generation resource and have to just rely on keeping, the coal or the nuclear running.
All right, here's a question that I'm not sure if we got time to answer it or not, but I'm going to give it a shot. Okay.
Oh boy.
Climate adaptation of the grid. What are projected needs to deal with hotter climate and worse heat waves, plus electrification and population growth?
Yeah. So this is kind of what I'm going to get into. I don't think heat waves are going to be necessarily our problem. I think heating loads are going to be our problem. The US, as we electrify buildings, the heat load, it's in general as a continent, the heat load is going to be greater than the cooling load, even during heat waves. So yes, we will need it in that transition time. Yeah, we don't necessarily even have enough capacity to manage the heat waves. Electrification, exactly, electrifying water heating and heating loads. A solution is what I'm talking about with passive building. We're cutting these loads in half before we electrify. So maybe we get to that.
Yeah, and I think what we do is we keep that in mind as we go through the rest of this presentation. Thank you, Tom.
Right.
All right, let's go to the next one, John. I think it's the very next slide. Meeting the daily electric load.
Sure. So basically, this is just trying to outline how, as the load increases, more and more expensive resources have to be called upon. So resource generation capacity bids into the market. Renewables are basically free after they're installed. Because the fuel, the sun, the wind is free. So those are generally called upon first, and then the less expensive to more expensive are called upon. So that last kilowatt hour of the day, or megawatt in this chart, is the most expensive.
All right, next, John.
So similarly, the cost of electricity is a very dynamic thing. Many of us have flat rates because that's essentially insurance to us to shield us from these spikes in cost of electricity. But really, at every moment, the cost of delivering electricity to a building is different based on the grid mix happening at that time. And you can see this chart on the right. As the demand increases, that vertical line, the cost of the supply increases, and it's not linear, right? When you get to a certain point, you're jumping to more expensive resources, and that's where you're getting into those peaker plants, those more expensive generation.
And if we do certain building right, we can help reduce that at least.
Right. So you're bringing the demand down, or you're making the demand able to see what the market price of the supply is at that time. So if the building could see, you see that chart on the right, the red line, if the building could see what the price was at each time, it could respond to when it wants to use a certain load at different times.
Gotcha.
Yeah, that is what we'll get into with GEB technology.
Let's go to the next one, John. Okay, this I find this interesting. I'm not sure I quite understand it, but go ahead. Tell us what we're looking at here.
Yeah.
Hourly marginal carbon emissions concept.
Yeah. So we just looked at how cost is different, right, at all times. That's because the generation mix, the resources we're using to meet a certain load on the grid, changes hourly, right? So depending on that mix, the emissions associated with that mix also changes. So what this chart is showing is the months of the year across the top and the hours in the day across the vertical. And certain hours of the year have different grid mixes than others. So red hours have dirtier grid mixes than green hours. It's basically in the easiest way to explain it. That's generally, at least for a market like Chicago, that this one is showing, there's either a higher peak or there's less, resource availability. I'm guessing the summer wind is what makes this green block here. We have a lot of wind energy in Illinois.
Okay.
That's what makes this summer wind block, the summer block at 5 p.m. and later, overnight wind greener. But basically, some hours using electricity is cleaner than others in terms of carbon emissions.
Why is November? I'm sorry.
Oh, no,
why is
okay.
November so high as opposed to December, January, February, your coldest months?
I'm not sure.
Okay.
Yeah, I'm not sure.
All right, let's move to the next one, John, which is going to be a typical simplified source energy accounting. So now, okay, I got you. But maybe the audience doesn't. All right, tell us what this is representing here, Lisa.
Yeah, so we just saw how dynamic the grid hours are in terms of actual emissions, but generally we just say, there's a source factor for electricity and this is it. And that's this brown blob, right? We're just like every hour is the same. So
everything's the same, whether we like it or not.
Yeah, and I should point out, because you asked about November versus, the summer. In grids like Illinois, when there's not a ton of renewables, like the hour to hour discrepancy, like the red to the green might not be that significant right now. But as we integrate more and more renewables, it's going to be very significant. So like somewhere like California, where there's a lot of renewables, there are definitely much cleaner hours than dirtier hours. So we're really like at the forefront of that, as we only have 14% renewables by 2030 or something.
This is our demand curve. In New
Yes.
England, this is. And ISO stands for?
Independent service operator. So this is one
Thank
of
you.
those, we saw the graphical regions in the beginning. This is one of those in the Northeast. So this is just pulling a random day. This was right before this presentation was given at summer camp. So I just pulled a random day, nothing special about it. Where you can see the forecasted load on the grid. The ISOs have this always, this website, you can go look at any day. You can see the actual load on the grid. It looks like those seasonal load profiles, right, that we saw for the summer, a peak right around the afternoon, and then what actually cleared the market. So this is just the demand on the grid.
Next. John?
And you can see then also not just the demand on the grid, but what they used, what the ISO used to meet that demand. So you can see those flat line base load at the bottom, the nuclear, the renewables, right, and the hydro. And then you can see the natural gas is the load following. So basically what I'm trying to represent here is this same exact type of thing happens day after day. The resources are used in a very predictable way based on the way they're able to respond to variances in building demand.
And natural gas is there for the peak because that's easier to ramp up and down. Is that accurate?
Exactly. Exactly.
Okay.
Those are, yep. It can respond
right.
to changes in load.
Let's go one more, John. I think that wraps up this section, and then we'll take a break for halftime and come back in and talk about how the grid is changing.
Sure. So this third one is newer. I think this was actually the first time I discovered this being on the ISO's website was for this presentation. And this is showing the actual load that the ISO thinks happened on that day. You can see kind of the faded load that the grid saw, that the ISO saw, but the orange line is the actual load they think they had based on behind the meter solar. So what this means is there's a significant amount of customers out there with solar on their roofs that is offsetting some of their energy use directly in the building before the grid has to supply the rest. So that's, the ISO can't actually see that when it's behind the meter. If it's in front of the meter, that means the utility can see it. If it's behind the meter, it means they can't. So this is part of the challenge that we're going to get into.
Okay, let's stop here. We're going to thank our sponsors for halftime. We'll be back with the second half. We've got a very interesting presentation with Lisa White, the Associate Director of Phius. Our marquee sponsor is First On Site, your trusted full-service disaster recovery and property restoration company at firstonsite.com. Association sponsors are ACGIH, Advancing Careers of Professionals in Environmental Health, Industrial Hygiene, and Safety, interested in defining their science. ACGIH.org. AIHA, Healthy Workplaces, A Healthier World. AIHA.org. The Cleaning Industry Research Institute. See more deeply through science and research. CIRI science.org. The IICRC, a nonprofit standards development and certifying body for the cleaning and restoration industry, IICRC.org. Industry sponsors are AEML Laboratories, free shipping, great pricing, same-day results with no rush fee, AEMLinc.com. Particles Plus, feature-rich particle counters and air quality instrumentation. Count on us. ParticlesPlus.com. TSI Inc., an industry leader in precision instrumentation for monitoring indoor air. Learn how to expand your IAQ investigations. TSI.com. Sunbelt Rentals, availability, reliability, and ease for all your IAQ and restoration needs at sunbeltrentals.com. April Air, healthy home, April, AIRE.com. And Healthy Indoors Magazine, a free online magazine for industry professionals and consumers, healthyindoors.com. All right, Lisa, let's jump right back into it. The grid is changing. Slide 21, John. What do we mean by the grid is changing, Lisa?
Yeah, so basically the grid hasn't been touched or redesigned in probably the 100+ years that it's been around. So there's kind of three main focuses, and one of the viewers pointed out electrification. So let's start there. So more things that we're using are being electrified. And a lot of this is due to this like movement toward decarbonization. If you electrify systems, then you can power them by renewable energy and use less carbon emissions. So we're electrifying vehicles and electrifying buildings for the most part. And buildings, most of the gas loads are heating and hot water that are being electrified, or cooking as well, but that's more minor. So they're electrifying things, and this is changing that seasonal load profile on the grid and changing the capacity that the grid needs. We're also decentralizing our resources. So I mentioned PV on rooftops. So generally right now we have generation, transmission lines, and then a building, right, using a load. And it's pretty predictable. One goes from one direction to the other. And the generation is always on one end and controlled by the central ISO. Now we have generation happening with consumers. So they're being prosumers, I think is what it's called. So they're generating energy all over. And it's not just the rooftop solar, but there's community solar, and there's smaller scale capacity and generation than we had before with these just centralized large fossil fuel based power plants. And then digitalizing. So kind of the whole world is digitalizing. It's not just the grid, but the grid is behind in terms of that. So basically newer grids or newer technologies are able to add signals or add responses, and there's smart grid technology. It's getting out there where you can maybe on a transmission line see if there's going to be a fault, or see where a transmission line is down, or preventative maintenance types thing, using kind of the technology that we've been using for years with computers and other things into the grid.
Okay, John, next. So now we talk about how the demand is changing too. Here's the demand trend.
Yeah, so I showed the New England ISO before. That's kind of an example of what the typical grid looks like. Not a lot of renewables. If you look at California, you can see the load is fairly similar. This is the same day as the New England ISO graph. Demand fairly similar. If you go to the next one, I think it'll show the net. Oh no, then the renewables trend in California.
Renewables is next, right? Okay.
There you go.
Go back to the renewables, John. There we go. Renewables trend looks like this. That's interesting.
Yeah, this is when the sun comes up. It's not a shocker. There's a lot of incentive for solar energy in California, and they have a lot of sun, right? So they have a lot of solar energy in the middle of the day. So then if you go to the next, you can see the net demand on the grid from that solar. So what the purple line is now what the grid is responsible for meeting, or the ISO. The California, they have their own ISO, the CAISO. And the challenge here is not that, there's a lot of renewable energy at certain points in the day. So those are those green points where that renewables trend popped up, where the solar is really high. Those are the green, clean hours of the day. And what's happening is when the sun goes down, the grid is now responsible for ramping up to meet what the load would be at that hour. When the sun goes down, the renewables aren't available. And you can see that 3-hour ramp. We talked about how different generation resources can only respond so quickly. You need certain resource types to be able to meet that ramp. And as we add more and more solar, this is called the duck curve. The belly of that duck in the middle right here around noon, that keeps getting lower and lower. And that ramp at the end of the day keeps getting higher and higher as we add more solar. Exactly, right there. So that ramp is the challenge, not just the ramp down, or not just the ramp up, but also the ramp down. So basically being able to respond to large amounts of solar energy in the middle of the day, the grid has to be able to have the resources to do that. And that's a lot of the challenge.
I think that's probably a huge challenge for, like I'm in a Somerset rural electric here, which is a little different than, some of the others. And it seems that would be a huge challenge for them, is to try and get those lines closer together, I guess. But yeah. Let's go to the next one, John. Transmission. Here's another issue. It's not just the grid is changing. There's transmission congestion. Talk to us a little bit about that.
Yeah. So this is from that same California ISO, same day, and it shows you where the congestion is happening on the wires, basically on the transmission lines, and how much renewable energy is curtailed each hour. It means renewable energy that's being produced that can't be used by buildings. So you can see it follows that same solar path, right? That yellow big blob in the middle of the day. And most of it is this economic local, this green, which means there's a market dispatch over generators with economic bids to mitigate local congestion. So I mentioned that the renewables always bid the lowest in the market because they're free, right? Almost free. They're very inexpensive to run. But there's local congestion on the transmission lines, meaning there's not enough actual capacity on the wires to bring the solar load to the demand. So the solar energy is being produced, but it's being curtailed. And those buildings are just using whatever other generation resources are available. And this is not a unique day either. I just picked the same day. This is happening day after day, sunny day in California. And you may see days where electricity prices go negative. This is why. It's better, or it's cheaper for utilities to pay you to use energy at that time because there's excess energy. Well, this is one reason why. One reason why that happens. So,
I'm just thinking, I'm sitting here thinking, I'm so glad I am not in charge of an electric utility out there today, or the transmission, or the grid itself. I mean, and with the way it's set up, it's a bunch of small kind of, what do you call them? Local organizations. I forget what they're called, but there's a bunch of them. And there's no real overarching, or is there some overarching group looking over the whole thing?
Yeah, there's FERC. There's regulation bodies. I wouldn't say there's necessarily one organization looking over the operations, but there are regulation bodies for the grid. But no, it's a big, challenging system. I'm not gonna say I envy that as well, and I don't operate the grid either. So I'm just trying to come at it from the building angle and understanding the challenges that we're having right now with very little renewables on the grid. And through what we're doing at Phius, we're trying to reduce our impact as buildings on the grid. And we're encouraging people to add rooftop solar. We're encouraging people to invest in renewables because we want to reduce the emissions of the electricity using the grid that they're using in the building. But we need to understand the other side of that too. And there might be other things we can do, such as grid enabled loads, which we'll hopefully get to, that can reduce emissions that aren't just adding more renewables. Adding more renewables, great, but we also need to be able to respond to use those renewables when they're available.
All right, let's go to slide 29, John. Zero impact, zero grid resilience, zero operating. This is where we want to go, I guess. Well, what do we talk about here? Net zero buildings, electrification movement, and dispatchable fossil fueled power generation. What's dispatchable?
Yeah, so this is kind of the main areas I would focus on from a building perspective of the decarbonization movement. So electrify everything, the electrification, I think you guys got that. Net zero buildings is basically offsetting as much energy as you're using on an annual basis with renewables. Many of people are doing this with photovoltaics on their roof. And then the third thing that's happening is dispatchable fossil fuel generation shifting to variable renewable resources. So dispatchable in this context is a resource that you can say, hey, turn up, turn down. I have control over the fuel. Variable renewable, obviously we don't have control over the sun, the wind. It's fairly predictable, but it's not necessarily controllable. So we have that shift of being able to control the supply at all times to having less control over the supply of our power if we're shifting to renewables, right?
And there's a range of net zero buildings. There's net zero ready, there's net zero buildings, there's net zero design buildings, there's net zero operating buildings. Can you talk a little bit about that?
Yeah, so let's start with net zero ready. That's kind of the lowest here, which is basically just having conduit or being ready to install PV on a roof. So you design the building, and in some year in the future, you can put photovoltaics on the roof and net out your annual energy use with solar.
And this is where DOE has been really, I think, placing a lot of emphasis there and trying to get new construction at least net zero ready.
Right. The zero energy ready home program. Right. And then zero energy, it depends. There's a lot of definitions, but generally it's just designing a building where you're offsetting as much as you're using on an annual basis. With Phius, we have a zero energy certification. And first you have to reduce all the loads in the building. We think that's super, super, super critical to going to net zero, you need to first cut all the loads using those passive building strategies, those charts we saw with the pushing down the space heating, space cooling, then add renewables to get to zero if you want to do zero. So then from that, other organizations do design versus verified. So design means you calculated it in a model, right? You calculated the building's energy use, you calculated the PV output, and those are at least equal or the PV output's more. And verified means it's operated generally for a year, showing that it's produced more energy on site than it's used over the course of the year.
Now, I noticed that you are a trainer in WUFI, the passive energy modeling software training. I've heard a lot of discussion about the fact that, you know, modeling doesn't necessarily give you what happens in the real world. What's your experience been? Has the modeling worked fairly well?
It actually has, yeah. So we've gotten data back from a fair amount of projects, and we're finding across the board, all climate zones, all building types. We don't have a huge data set, but it's roughly within 7% modeling versus measured, which is pretty good. Obviously, there's some that are off by 20%, you know, some that are performing better than the model by 10%. It depends, right? But across the board, it's working pretty well, and it's pretty consistent. Yeah, so we do, these are Phius certified projects that I'm talking about comparing to models. So there is a ton of oversight on reviewing the energy model, making sure it actually matches the plans. And then there's some testing required when the building's finally built, and you have to put that back into the model. So we're making a decent amount of effort to make sure the model is actually matching what's built, and putting a decent amount of effort into quality assurance during the construction process to make sure the design matches what's built. So it's a really quality assured process. So I think that's a lot of the reason the models match the buildings pretty well.
Okay, John, let's jump to slide 43. Not all kilowatt hours used are produced equally. I think that's an important point. There we go.
Yeah, so we talked about net zero and how it's like over the course of the year, I am using less than I'm producing over the course of the year. But we have to think about when energy is being produced and when energy is being used, if that net zero is actually, you know, valid. It's not like the building is, so you were talking about the other side where it's like, it doesn't mean it's zero emissions. It doesn't mean it's not using the grid, like this net zero concept. It means over the course of the year. So you could be using energy during the red hours and producing energy during the green hours. So if you were to net out those numbers, it wouldn't quite be net zero.
And you could be producing energy when it's not needed as much. And that's what you're trying to do, is kind of match that up better.
Yeah, or at least, you know, change the accounting or use more energy during the green hours and shift energy away from the red hours, right? And enable the building to know what's a green hour versus what's a red hour.
Would the other or be to get better ways of storing energy?
Yeah, absolutely. Energy storage would help for sure, especially if you have on-site PV. So you can store energy or store excess PV during the day, excess solar energy during the day, and then use it throughout the night. Absolutely would help. Really, storage is just another mechanism for grid integrated buildings, which we haven't quite gotten into yet, but enables you to move your load around. Yeah.
All right, John, let's go to the next slide. And it's basically, I think we covered this. We're talking about how much instead of when.
Right. Shifting to no green hours versus red hours.
One more, John. Now we're there. All right, here's your big topic: grid interactive, efficient building.
Right.
Talk to us about this, Lisa.
Yeah, so the acronym is GEB. Go back one more.
Go back.
There we go. And it's enabling the building loads to be smart and responsive to signals. So right now the building just uses, you know, electricity whenever it needs electricity. But if it knew the red hours, knew the green hours, knew the price signal, the building could actually shape that load, right? It could say, you know, maybe I pre-cool or preheat my space if I know it's cleaner energy in this hour block than this hour block. So it's using the digitization aspect of the grid changing to make the building grid interactive. And the efficient part's really important. Phius does that, but it's really important to have an efficient building to enable these things to work.
And is anybody doing this now?
There are some. It's very early in stages. The DOE did release a GEB roadmap. There's a couple case studies. I can't say there's any Phius projects that I'm aware of. We're working on it, trying to kind of combine these two, and that's really, really where you see the benefit, combining the passive building enclosure with these techniques of shedding and shifting loads, because the passive building enclosure is basically another form of energy storage, thermal energy storage rather than like battery or electrical energy storage, where it's really easy to shift loads from the green hours to the red hours. And
interesting.
Sorry,
Next
other
slide.
way around.
Next slide.
Red green. Yeah.
This is what it looks like at the building level.
Right. The different types of things you could integrate with the controls. So there's this control system telling you when to use energy and when not to. Price signal on the grid would work as well. It's very closely associated with emissions. But you could change your HVAC, change your set points, dim your lighting. Maybe some plug loads, like phantom loads, you could turn off. PV and storage and EV charging. If your EV is going to be plugged in all day, but maybe it could only, it only needs 6 hours to charge. Let's have it pick those 6 green hours, right? Instead of just right when it's plugged in, because maybe those are red hours. So all of these different controls. And this is generally at the building level, and the utility could control that.
And this would also, I think it could be set up in a way where the consumer could take a more active role in trying to reduce their costs even.
Absolutely. And that's a big reason. Right now it's hard because the difference in cost, a lot of people have flat rate electricity costs. So that's one thing. When you have time of use costs, that absolutely you can save money by shifting energy use to different hours of cheaper electricity.
Is that where we're headed? Are we going to see time of use costs?
I hope so. I really hope so. A lot of utilities, you can pick it. I'm with ComEd. We could pick time of use energy costs. They don't care. There's no like, nothing that would set them back from doing that, because you're just paying whatever it costs them, right?
Okay.
So, yeah.
Interesting. Let's go to the next one, John. GEB grid interactive. Wait, what it looks like load shifting and shedding. I just thought maybe we'd touch on this real quick since we're running a little low.
Yeah, no problem. So this is really important. So this is some of the toolkit measures for a grid interactive efficient building. GEB, that's what it's called. So load shifting, if we look at an hour of the day, is basically taking a load that needs to occur and shifting it to a different time of the day. So this could be pre-cooling or preheating a space. If you know that there's going to be a peak later in the day, move it to the morning, so you have more of a flat load, or moving from basically red hours to green hours. This could also be appliances, your dishwasher, running your clothes washer, things that need to happen but don't need to necessarily happen at that time. And then load shedding is actually just removing or shedding a load during a peak. So this could also be space conditioning. This is probably almost always space conditioning or lighting dimming, where you're peaking in a building and you're like, okay, I'm going to turn my thermostat back and or turn my heating system off, turn my cooling system off to shed the load at that time, because it's about to hit a really expensive or really high carbon emissions peak. And that's what passive buildings are really good at doing, shedding loads. Okay. We've done a lot of resiliency studies where it can be without heat or cooling, for mostly heat, for days and remain survivable. So a few hours, even on turning a heating system off in a passive building, even in somewhere like Chicago, not a big deal in terms of comfort. So really inherent quality of passive. Yeah.
If it's built right in the first place. Let's go to the next one, John. This is where you kind of tie together GEB and passive building.
Yep. So generally we have the power flow going one direction, and it's based on whatever the customer load is saying it needs. So GEB could be the grid. If you look on the left, the grid stress is really high. They're peaking. So they would signal to the customer to reduce the load, and the building would respond and reduce the load. So there's some sort of signal happening from the grid to the building. Generally, I think we skipped this slide earlier. In the typical grid, it would be the customer load, that top arrow, just telling the grid to turn up. And even if it's all the way red like this, it needs to turn up even more, right? It needs to get more and more peak. And the customer doesn't see anything from the grid in terms of the stress signal or the price.
All right, let's go to slide 52, John. I think this is important. And then after this, Lisa, I'm going to break for, we do what we call a roundup. Can you stay an extra 5 minutes? I think we can get this all in if you can.
No problem. Yep.
The peak is changing. Winter is coming, Lisa. What do you mean?
So we kind of talked about this earlier, where the peak on the grid right now is in the summer due to space conditioning loads, cooling loads. But we're starting to electrify buildings. We're starting to electrify heating loads. So the peak is shifting from the summer to the winter. And if you think about a typical building, I made up numbers here, the peak is 4. And then if you use passive building strategies, you can get the peak down to 2, right? So if we think about the capacity needed to meet a peak of 4 versus a peak of 2, it's at least double, plus redundancy and reliability factors. So almost that factor of 2.5 to 3 that we talked about with capacity versus peak.
Interesting. All right, let's go to the roundup, John. The roundup is brought to you by April Air, providing healthy humidity, ventilation, and air purity solutions for new and existing homes. April Air, healthy home at aprilaire.com. Okay, hey, John, can you pull up slide 58? And while you're doing that, I want to ask Cliff, the Z-Man. Cliff, you have any follow-ups or any questions?
Yeah, I do actually. Something interesting happened earlier this year. I think it was probably driven by the war in Ukraine and energy exports from Russia, being reduced. But that young gal, Greta Thunberg, and she actually called for Germany to not shut down their nuclear power. So I guess what my question is, what's the role of nuclear in this? Because it seems like it's a pretty simple, viable option that, you don't need batteries. I mean, if you can make it cheap enough, you don't need batteries to store it. You don't need all the, voltaic systems up on roofs and so on and so forth. Why not nuclear?
Yeah, I wouldn't necessarily say no nuclear. So nuclear is kind of in between this renewables and the fossil fuel base because it doesn't have carbon emissions, but there's still waste. There's still nuclear waste, whereas renewables, there's not this very toxic waste. But nuclear, we couldn't run on nuclear alone because nuclear cannot respond to big changes or big dips in energy use. So it wouldn't be a good resource that could accompany like a solar system or wind, because of how spiky that is, right? And because of how much that changes. Nuclear just really wants to be a flat load. But I think it's going to play a large role in meeting that base load of the grid as we transition some of those other resources, coal and natural gas, off the grid. Nuclear can stay there and meet the base load and not actually have carbon emissions associated with it. The other thing that's has to be considered is like the lifetime of these power plants. So in terms of financing them, they're generally on 40-year cycles, and a lot of them are retiring or getting up to getting up to expiring. So you either need to reinvest for the next 40 years or retire the plant. So they're at kind of a critical moment where they have to make that decision. And it's really, really costly to put that investment to have that around the next 40 years or you retire it. So I don't know the answers, but I don't think it's going to be going away immediately.
Interesting.
Fair enough.
Let's go to the microgrid, slide 58, John, because this is something we hear a lot about, Lisa, microgrids, and you have a little different look at it, a little way of looking at it. Why don't you go ahead and talk to us about this one?
Sure. So a microgrid is basically a cluster of buildings that are GEBs or have grid enabled loads. And instead of just being the central generation resource to the building, there's interconnectivity between the building and communication between the buildings. And there's a central system that can control that. So that it's called a microgrid manager. So that knows basically what are the red hours, what are the green hours, what's the cost, what's the generation resources available, what's the energy storage. So microgrid is a combination of these buildings with these smart loads, some sort of energy generation, some sort of energy storage, ideally renewable energy generation and energy storage. And then this kind of optimizer that's saying, I have this kilowatt hour available. Do I meet this building load? Do I store it? Is every building satisfied? Or they don't have energy available and maybe it taps into the storage capacity, or they're connected to the main grid. So maybe then it pulls from the main grid during those times. But it's really taking smaller parts of the grid and making them smarter, and optimizing within little chunks of the grid.
Is there anywhere we're doing this now?
Yeah, there definitely are some. I think microgrids have existed for a while with the military or things related to like defense, just for security. But there are places, I think in California, that are doing this. There's a lot of pilot projects. I believe there's one in Maryland. I could try to think of this. There's one in Chicago, actually at IIT, our campus here in Chicago, small microgrid for a campus. It's more common within campuses as well, like university campuses where they'll generate energy and have like thermal energy networks or gas or steam systems. It's similar to that.
What about some of these large, like Twitter and Facebook and Meta or whatever they are? Do any of them trying to work on a microgrid for their own?
I have no idea.
Okay.
I would imagine eventually, because that just seems that would be the way that type of company techies would go. And it makes a lot of sense, especially companies that have committed to different carbon emission drawdown, goals, or meeting, certain reductions in emissions. If they can do that on their campus and figure out how to fully utilize renewable resources, that would be a big step.
Interesting. John, let's go to slide 65 and just kind of quickly review the microgrid benefits here.
So we talked about transmission congestion and the wires, right? And those not being able to carry the load sometimes. So microgrids bring the generation closer to the load. So we need less updates in the transmission infrastructure. If the grid goes down, the main grid goes down, generally there's also an option or a disconnect between the microgrid and the grid for the microgrid to island. That reminds me of another microgrid. There's a community in Florida that is a microgrid community, and they were fine.
Yeah, I saw that.
Yeah, throughout this recent hurricane. So that's a huge opportunity for resilience. And microgrids in general, huge opportunity for resilience, having all these different little pockets rather than having a central system that's vulnerable to weather and climate and natural disasters.
Well, and maybe terrorism too, right?
Absolutely. National security issues for sure. Absolutely. Making more than one large target, right? Little splitting things up. So improved renewable resource utilization, having that optimization within this little group or little grid allows you to utilize the renewables when it's available more than we're able to do on the large grid. And I mentioned optimizing smaller areas of the grid, but this is also alleviating the stress on the large grid. We talked about that peak and all the capacity, and then the fact that could double, triple with electric vehicles and electrification of buildings. We're going to run into capacity issues very quickly. So if we can help alleviate the stress and the capacity needed on the central grid by optimizing little pieces at a time, it's a big benefit. And the last one, I personally am very kind of excited about is energy independence. So allowing for communities to have independence and no vulnerability to fuel prices from wherever your fuel sources is. You mentioned the war in Europe and the vulnerability to being cut off from a fuel supply and how greatly that impacts a country, a community. Being able to generate and use your own energy on site and reduce that vulnerability to energy pricing or energy sources is just huge. To me, not just for less cost, but also just general control of power right across the world. So I'm really excited about that piece of it, being able to harness free solar or wind energy and communities being able to power on that. Yeah.
John, let's go to 67. These are more proposed solutions on optimization at each level now. So you're kind of tying things together here, I believe.
Yep. Sorry, it's a long presentation.
No problem.
So passive building optimizes at the building level, reduce the loads, use the passive strategies, right? And it also not just reduces the loads, but reduces the renewable capacity required to meet that load. Then you make those loads smart. Whatever loads you have left with the passive building, make them smart, enable those loads or that demand, the load or the demand to align with when the supply is available, ideally the clean supply. And then the microgrid is taking a bunch of those grid-enabled smart passive buildings, and then optimizing the supply and the demand, maximizing the use of that renewable infrastructure, and minimizing total emissions. This is how I look at it. I will say microgrids in general aren't only designed to reduce emissions or maximize resource availability of renewables. A lot of them are for security and resilience. That's a main motivator for all the ones that exist today, to my knowledge. But I think it's a really great opportunity to be able to harness and kind of harden more renewables, meaning increase the utilization factor of renewables that we're adding.
John.
Yeah.
Next slide. I think we had a little more. Okay, so this kind of is the visual of it, huh?
Yeah, it's a lot going on here. But basically, this is trying to show that there will be a digital connection between these things, where there's signals throughout either the storage, the generation. There could be a virtual market where you could bid into the market and say, I'm willing to turn my thermostat off, and that will reduce my peak by whatever, 1 kilowatt. And I can bid that into the market at a cost. And actually, the grid independent service operator could call on you to do that in the same way they'd call on more natural gas to ramp up, right? So there's this like interconnected market where the demand enabled, the grid enabled demand can actually be part of the generation or used in the same way. So the smart communication between everything can really optimize the whole picture. And right now we don't have this.
And let's finish with 73, which is kind of, you're tying it all together once again, the ripple effects of conservation.
Yeah,
This
I like to talk about this.
So sweet.
I like to talk about this. Yeah, go ahead. Sorry.
Well, it's like, people wonder about, using less energy, and the first thing you've got to do is concentrate on using less energy, not using cheaper energy. And I think this is kind of where you're headed in, but on a bigger scale. Right.
So I always like to point this out because there is a ripple effect of conservation beyond simple payback in buildings. So often we think about, okay, I put this level of investment in conserving energy in my building and it's going to pay back over time because this is what electricity costs, right? That's how we think about how do I invest, like, because I'll save over time, great. But if you think beyond the building, right, and we think about this renewable energy transition, we're adding more renewables to meet that load. We're adding energy storage to make that renewable energy more dispatchable or make it available when we need it. And then we also have to have transmission that carries the renewable energy to and from the building. If you reduce that, first, the building energy load by 40% in this case, which is typical of a passive building, you also reduce the renewables needed by 40%, the energy storage capacity needed by 40%, and the transmission capacity needed by 40%. Not to mention other things, but this ripples through the system. When you start with looking at just reducing the demand side, it ripples all the way through and saves a lot more than just, yeah, I saved this on my utility bill. It's a system-wide effect.
Fantastic. Lisa, that was excellent. And we did it in 1 hour and 10 minutes. And I think once we make a few edits, we might have it down to 1 hour and 8. It was wonderful. And we did more than what you did at summer camp. So somehow we pulled it together. Thank you for joining us.
Thank you,
Cliff, before we go, any final thoughts, questions for Lisa?
No, I'm good. Thank you, Joe. Thank you.
Lisa, I just want to give you my last question I give everyone. And that is there anything we missed that you'd like to add? Any final thoughts?
Kind of, but I'm not sure I can add it. We talked about the winter peak, and I just want to point this out once more. We looked at the one building of a winter peak going from 4 to 2 with passive buildings. I want to make sure people understand that when you start to group this into more and more buildings, that capacity requirement is multiplied. And then when you make those loads smart with the passive buildings, you can basically exponentially reduce the grid capacity needed to meet the same buildings. Once you reduce the load first and then make the load smart, there's this like exponential effect or synergy between first doing the passive buildings, then making the load smart, then managing the loads between the buildings. And in this presentation, I think I showed it going from 36 down to 3 in terms of like the peak on the grid at that time. Just by tapping into each thing individually, it becomes greater than the sum of the parts. So that I want to make sure that's a takeaway. because I think it's really important. And it's a really big place where passive building plays a role.
Thinking big, Lisa. Thinking big. I love it. Thank you so much for joining us. I'd love to get you back sometime and just go into a little more detail about Passive House and Phius and the
Absolutely.
requirements and so on, and why you have those requirements. And we'd love to get you back. This is Radio Joe saying thanks to Lisa White, my co-host, the Z-Man, Cliff Zlotnick. John, you got to have faith at the controls. Most importantly, our growing audience and sponsors, we really appreciate. By the way, next week we've got a good one. Dr. Joe Allen will be here. We're going to talk about some revisions to his book and get into the White House IAQ Summit and some other things. So please come back and join us next Friday at noon for the next episode of IAQ Radio Plus.
For IAQ Radio, I'm Spike Reel saying thanks for listening.